Good afternoon, everyone. And first of all, I'd like to thank the organizing committee of APS satellite meeting at ICTS and for giving me the opportunity to present my work on stacking order driven optical properties and layer parity dependent Phonon modes in RES2. So today I'm going to talk about the work on rhenium disulfide, which is a kind of TMDs. But you can say this is a special kind of TMDs. Why it is special? Due to its extra one valence electron in d orbitals of rhenium, there is extra bond in RE, and due to this extra bond, the structure there is a distortion in the structure, and that distortion is called the pulse distortion. And due to this structural anisotropy, their properties like electronic, optical, and vibrational properties also shows the anisotropic in directional. And apart from the traditional TMDs, there is another uniqueness, that is the weak interlayer coupling strength in these materials. And if you compare the interlayer coupling strength between MOS2 and RES2, you can see the value is very, very low for the case of RES2. And due to that, if you look into the band structure of RES2, you can see the band gap of monolayer to bilayer, it is almost unchanged. Not only that, you can see the direct band gap from monolayer to bulk. And due to this interlayer, weak interlayer coupling strength, there is a challenge to find the exact stacking order of multilayer or bilayer. And people already in the literature, they have all suggested few stacking order, but still we thought that there is a opening challenge to find exact stacking order of multilayer RES2. So with this motivation, we have started the work. And first we have displaced this is the bilayer RES2. We have displaced the top layer RES2 in this particular direction, and we got this kind of potential energy surface. And you can see here that there are two basically minima. And if you compare the energy is lowest for the case of AB stacking. But we have considered both this stacking, and and this stacking we named as a AA stacking, and this is the AB stacking. Here, for the case of AA stacking, thus exactly the top layer sit on exactly on top of the bottom layer. But after relaxation, we have found that there is very little bit displacement is there with respect to bottom. Not only that, for the case of AB stacking, we found this is a stacking where the displacement around 2.5 Armstrong with respect to bottom in this particular directions. And whenever we have also compare our result to our experimental collaborators, you can see these bright dots are coming due to the rhenium, basically rhenium, and you can see there is array of rhenium atom, and that corresponds to the RE chain. Basically, this is the B directions. So whenever we have seen that these two stacking, whatever we have proposed, that are actually their experimental also experimental stacking orders. And so from this slide, we can understand that not only means actually there is a weak interlayer coupling strength that is there, but there is quite high barrier, and that separates that two stacking order. So that's why this stacking order should be means behave in different way to check their to further check their stacking order and further confirmation. We have also carried out the Raman spectra calculations. So you can see here that these two are the two characteristic modes. This is the first one is the out of plane modes, and this mode 3 is the in plane modes. So if you look into this around 150 centimeter inverse, this mode, there is no shift of AA or AB stacking, but there is shift of AB stacking modes with respect AB stacking peaks corresponding to AA. So it is quite obvious because this is the out of plane mode. So whenever you change the stacking order, there is a shift should be there in the out of plane mode. So that is observed, and the difference is the difference between these two modes quite matching with our experimental result, that is 13 centimeter inverse and 20 centimeter inverse, and that again confirm our stacking order. After this, we look into the low frequency Raman modes, because low frequency Raman modes gives you the informations of the interlayer coupling strength and also anisotropy. We have found that for the case of MOS2 or WS2, you can see the shearing mode, there is a degenerate shearing modes, both the shearing mode in the same peak position. But here you can see the splitting, basically shearing perpendicular and shearing parallel are vibrate in basically our peak position are different. So that's why there is an anisotropy in the structures. Not only that, you can observe another thing, that for the case of AB stacking, the peaks are in higher energy compared to AA stacking. That again confirm that for the case of AB stacking, the interlayer coupling strength is more. So that's why we have seen in the previous slide that the energy corresponding to AB is lower than AA. And we have again further checked this thing, that the interlayer distance for the case of AB stacking is lower compared to AA. And that confirm the stronger interlayer coupling strength AB compared to AA. After that, we have calculated the optical absorptions using GWBSC approximations. We have found, so as we have mentioned, that both the stacking has both the structures has the anisotropy that you can see here from this is the optical absorptions in one direction, and this is the perpendicular direction. Basically, one is area-reach-n direction, and this is the perpendicular to area-reach-n direction. So if you see both this plot, you can specifically understand this thing, that for the case of AB stacking, the anisotropy is more. Not only that, in this spectra we have observed three characteristic excitons, exciton 1, exciton 2, and exciton 3. And from the experimental evidence also, we found that for the case of exciton 3, the transition probability is high in AB stacking compared to AA stacking. That we got the value here, that the oscillator strength corresponding to exciton 3 is more compared to AA stacking. To understand this result, we have calculated orbitalism band structure, and it was found that the exciton 3 is originated due to from the transitions gamma point at VBM to CBM, and that is 5D basically 5D T2G orbitals to SP S3P orbitals. So we have, whenever we have checked the orbital contribution, it is found that for the case of VBM, the contribution is at around 1.5 times more than the contribution from AA stacking. For the CBM case also, the contribution of 3P orbital is around 1.2 times more than the AA stacking. And we thought that this and that's why the carriers are more in this transition. So that's why the transition probability is high. Another thing we also we explained that in the previous slide, that the interlayer distance is lower in case of AB stacking. Interlayer coupling strength also is high. That means the screening effect in the system is high compared to the this stacking. That means due to this higher screening, the excitonic binding energy is also low, and excitons are delocalized, basically more delocalized in case of AB stacking compared to AA stacking, and that leads to the faster recombinations of exciton 3 compared to AA stacking. That is also one of the experimental observations. After that, I have already talked that in RES2 there is an anisotropy, and due to very low symmetry, actually we got 18 Raman modes there. And as there is a very low interlayer coupling strength between the layer, people said that means this layer can be acted as a basically independent layer, and there means means from monolayer to bulk you can get only the 18 modes. But few literature also suggested that whenever you go from monolayer to bilayer to trilayer or so on, you can get extra modes. And that is also, and they have explained this thing, that due to the defect activated IR modes or due to the double resonance, these extra peaks or the splitting of peaks may be coming. But we have, but that is not the reason, because we have checked in our HRTEM result that there is no defects, and in our calculations also we have not introduced any defect in the system. So I will show in the next slide. But still we are getting the extra peak and also the peak splitting in the system. And double resonance is not also possible, because in this literature they have claimed that only 785 nanometer, this whenever they use this source, only in that time only they are getting the extra peaks or the basically peak splitting. But in our experimental results, we have found that other than this source, whenever we use different frequency source also, in that time also we get extra peaks and double peaks. So extra peak and peak splitting. That's why we discarded these 2 points, and we move forward, and we have calculated the Raman modes for bilayer, trilayer, 4-layer, and so on. And we have, you can see here that for bilayer itself, you can get the extra mode below the AG1. And if you, and these 2 modes are consistent throughout all the basically multi-layer. And so from here you can conclude one thing, that that there is still finite interlayer coupling between the layers. So you cannot consider this layer as an independent layer. Whenever we go from bilayer to trilayer, you can see there is a peak splitting in the easy modes. And whenever we go from trilayer to 4-layer, you can see this splitting disappear. There is there is no splitting in this modes. Okay, so from the experimentally also, you can see from here to here, when we get actually extra modes and also peak splitting. Okay, and this our possible the origin of this extra peak and peak splitting may be we have given that whenever we move from monolayer to bilayer, the first in monolayer the inversion symmetry is here. Okay, so in that case there is crystallographically 2 Re atom, 2 independent Re atom. When we go from monolayer to bulk, the inversion center move from here to here, and in this case, in bilayer case, there is now there are 4 crystallographically independent Re atom, and that apparently change the symmetry in the structure, although there is inversion symmetry is there. So that's why we got these extra peaks throughout the range. And for the case of trilayer or basically odd layer, you can see this splitting, and that is due to the breaking of inversion symmetry. We have checked that for the odd layer, the inversion symmetry has been broken, and due to that, the extra peaks. So with this, I would like to conclude the talk. So first of all, we have identified 2 stacking orders which are stable, and basically there is finite interlayer coupling strength. Further, with vibrational modes also we have confirmed that AB stacking is more anisotropic, and it has the more interlayer coupling strength than AA stacking. And then we have also concluded this thing that for the case of AB stacking, the excitons are more delocalized, and there is faster recombination in case of AB stacking. And at the last, we have discussed about the origin of extra Raman modes in multi-layer RES2. With that, so in this, due to shortage of time, I have only covered a few of my key results. So interested people can visit this paper. And for this work, first of all, I'd like to acknowledge my professor, my supervisor, Professor Abhishek Kumar Singh, and Professor Guwang and Professor Pamoda for their valuable comment and suggestions, and Prongsu and Injung for their experimental supports. For this work, I have used computational facility from MRC, SCRC, TUE. And with that, I'd like to thank all the audience, and I'll be happy to take your questions.
Right, so we can have a couple of quick questions. Okay, I have a quick question. So in the stacking order things that you were talking about, was it just bilayer or was it multi-layer that you were talking about when you said the stackings in the beginning?
Yes,
first figure.
Sir, for this case, we have went up to 5 layer, and we have seen that AB stacking is remain there and AA stacking also is there. So
there is, in most of these TMDC systems, there is a sublayer, there's a sublattice symmetry breaking, which leads to a stacking near 0 and an R-type stacking as well. Is that something similar that can happen here as well, or because the lattice is not hexagonal here, it doesn't happen?
Sir, I think due to the weak interlayer coupling strength is the reason.
The lattice is hexagonal here, or is it?
Yes, hexagonal. But the lattice actually lattice constant double of the most traditional.
Okay.
So,
you said it's slightly off the stacking, right?
Yes. So, ma'am, actually, whenever we relax, because we thought that may be the reason that sulfur on top of sulfur, and that I think the sulfur PZ orbital repel to each other. That's why there is slightly basically their displacement is there.
So the symmetry is broken.
No, and so for bulk also, whenever we checked that there is no changes or whatever 120-degree angle AB is there, but for the case of gamma, basically gamma, we have checked that this is not exactly 90-degree. So that's and I think and that actually preserve the symmetry, inversion symmetry in the structure. If the stacking exactly on top of basically A stacking, then it will, this inversion symmetry is not there. So no, for AB case inversion symmetry is not there. For AA case inversion symmetry is there, still there. So whatever the Raman result I have shown in the last basically multi-layer, that is only for A. No.
Okay. If there are you have a question? Okay. If there are no further questions, let's thank the speaker again. And